introduction, and thank you for the got it. And thank you for the invitation. It's nice to be with you virtually, at least. So this is going to be about a joint work with Giorgio Stefani. So he used to be for a couple of years a postdoc here in Basel. Now we moved and is at SISSA in Trieste. So it's back to Italy. So like half of the talk will be about our new result, but I will also give a sort of overview about this Yudovich theory for the two-dimensional Euler equation. So there will be a sort of, say, gentle introduction to the topic. Let's see whether I can move to the next slide. Fantastic. Okay, so these are the Euler equations. So V is the velocity, P is the pressure. So they are homogeneous. So in the sense the density is identically equal to 1. So and inviscid, so no viscosity. So this is Euler and not Navier-Stokes. So they're incompressible. So we are enforcing the constraint. Divergence is equal to 0. And therefore we have the pressure, which is a sort of Lagrange multiplier in a sense. So this is in general dimension. So this velocity form of the equation. 2D is very, very special. And this one also sees in the physics quite a lot. And one of the mathematical reasons is that in 2D, we have the vorticity omega defined as the curl, the rotational of the velocity field, which is a scalar or can be identified to a scalar, and satisfies a very special form of the equation. So satisfies this advection equation, so a transport equation. So omega is transported by the velocity v of the fluid. But of course, the nonlinearity of the equation does not get lost, of the other equations, does not get lost, in that the velocity and the vorticity are coupled by this integral relation, the so-called Biot-Savart law. Okay, so in order to recover the velocity, you convolve the vorticity with this mildly singular kernel in R2. And today, so my focus will be for this two-dimensional problem on uniqueness and non-uniqueness under assumptions on omega. So you can play different games. So you can look at the equation in velocity and then discuss existence and uniqueness depending on the regularity of the velocity. But we will do something, classical, but different from that. So we discuss uniqueness under assumptions on the vorticity omega. So this is very special in 2D in a certain sense, because, so for instance, you see that at least formally, this equation here being an advection equation by a divergence-free vector field preserves formally all LP norms, all Casimirs of the solution, okay? So you can start, playing with spaces in which the vorticity lives because they are conserving in time. So the two sides, in a sense, the good and the bad. So uniqueness, so Yudovich showed uniqueness for solutions which are L infinity in space, uniformly in time, or with some mild growth of the LP norms. I will comment a little, so quite detailed in the following, what we mean by that. So, and another landmark result was due to Vichik, so some years after Yudovich. He was able to prove uniqueness in BMO-like spaces, so bounded mean oscillations. And there the theory also becomes way more complicated. So it's no longer just PDE estimates, but kind of quite stronger use of harmonic analysis. And the theory becomes also difficult because there is one space for uniqueness, but then it's not easy to prove existence within that space. And this opened the way for many other contributions of people around Bernicot and many other authors for spaces in which one has well-posedness in the sense at the same time existence and uniqueness. So non-uniqueness is also quite a vivid and pretty nice, in fact, field, so area of research at the moment. So a few years ago, Vichik showed non-uniqueness for LP vorticities for any p less than infinity, but at the price that you have to add a forcing on the right-hand side of the equation. Bressan and collaborators, they also started a pretty nice project in which they had some kind of physical intuition of what a setting in which one should have non-uniqueness could be. And they had a proof which is partly analytical and partly, basically computer assisted or with solid numerics in a sense, but still not a full analytical proof. And even more recently, so Bru and Colombo, they showed that, so via convex integration, that if you go to spaces which are a bit below L1, so these Weak-Lebesgue spaces, Lorentz spaces, you can produce non-unique solutions by convex integration without any forcing on the right-hand side. Okay? This is for completeness, so I will focus on the uniqueness in the rest of the talk. And the strategy of Yudovich is that of doing an estimate for the relative energy. So the relative kinetic energy is the following. So it's the squared L2 distance between two velocities, okay, with 1/2, because we want the physical kinetic energy. So density is constantly 1. Great. So you have two solutions. You want to show uniqueness. So V1, V2, they have associated pressures, P1, P2, and then you take the difference between those two equations, and then you do an energy estimate on the equation for the difference, and you get the following. So the time derivative of the relative kinetic energy is controlled by the integral of the gradient of one of the two solutions times the square difference of the other two velocities, two solutions. So now the observation is, if we had that the gradient of V1 is L infinity, so if we had that one of the two velocity is Lipschitz, then easy peasy. So we can simply do a very simple ground wall and conclude the proof. But V is given as via the Biot-Savart law, so K star omega. So the gradient of V is the gradient of K convolution with omega. And now gradient of K is really singular. So it's a Calderon-Zygmund singular integral operator. And in particular, so these operators, they behave well on LP for P not equal to 1 and to infinity. So we have a little bit of a problem. Nevertheless, there is one additional information. So they behave nicely. So these Calderon-Zygmund operators on LP spaces for P less than infinity. And they behave nicely in that there is also a quantitative, there is a quantification of the constant in the operator norm depending on P, and it goes like P. Okay, so then if we have a vorticity in L infinity, we can estimate the gradient of V in LP with P times the L infinity norm of the vorticity. In particular, if you look again in physical space variables, this reflects into the fact that the velocity is not Lipschitz, but as this logarithmic degeneracy. So the velocity is what is said log Lipschitz and not Lipschitz. Okay, it's a little bit worse. Great. So there are two tricks Yudovich used in the two different papers, in fact. So in the first one, so we go back to this estimate we had here. So E prime controlled by grad V1 times square difference of the velocities. And then you decide, okay, let's split, you know. So gradient of V1, we estimated in LP, think of P large. And then we put the dual P prime, on the difference of velocity squared, and also that we split. So a little in L infinity, a little in LP prime. The point being the velocities are uniformly bounded in L infinity. If the vorticities are in LP with P larger than 2, then this goes into a constant. This I chose here things in such a way that I get again some relative energy. And then I have this quantity here in front, which is controlled by C times P because of the Calderon-Zygmund inequality, the quantification of the norm. And then all in all, I obtain the following. So E prime controlled by C P E to the 1 minus 1 over P. Okay, basically now I cannot do anything at fixed P, but I can think of optimizing in P, or something which is very similar. For P fixed but finite, I consider the maximal solution, which is just this function here, Ct to the P. And then, at least for short times, so T less than 1 over 2C, I can send P to infinity, and I get that the energy has to be equal to 0, okay? So you have short time uniqueness, but then I can restart from any later time, and how short it's universal, okay? So this is uniqueness for the equation. If omega is in LP, although I don't have a classical ground wall argument for that. So this was Yudovich's first paper on this topic. And the second one, okay, so now we'll tell you what is in the second one, which is rather cute. And this will also say what, so we'll explain what mild growth of the LP norms mean. So we assume that the vorticity is in all LP spaces, but L infinity. And we say that, okay, we define this function theta of P, the LP norm of the given vorticity as a function of P. And we assume it grows sort of slowly. So we see which slowliness we will need in a while. So we played the game that we played before of like some large LP norm here. So now I just, for convenience, I pick like P of the form 1 over epsilon. So with epsilon small now. So here a large LP norm, here the dual, and then a piece in L infinity. And then I play like before. Okay, I use again the fact that Calderon-Zygmund now has a constant 1 over epsilon, and I obtain this, okay, which corresponds to what we've done before, modulo, switching LP and L1 over epsilon. Okay, but now in this form, I just rewrite, okay, just rewriting in this way. So omega in L whatever is controlled by theta of whatever. Okay, this is my assumption, mild growth. Theta is the function on which I will put conditions rather soon. And here I just take out, so one energy, E of t, from the 1 year, and then minus epsilon here, okay? Just to be able to write the thing in the following way. So if now we have again an estimate, which depends on a parameter on the right-hand side, and then I take the best estimate. So I infimize in epsilon. I define this function psi, which depends on theta. And then I get the following differential inequality, E prime controlled by C times E, which would be great for ground wall, times psi of 1 over E. Then, okay, we don't apply ground wall, or Yudovich didn't apply ground wall, applied Osgood. So Osgood is a condition giving uniqueness for an ordinary differential equation, so starting from a critical point, from a 0. So under this condition here on the function psi, one has uniqueness. So the condition on the function psi, well, the function psi is defined in terms of the function theta, so reflects very implicitly, that's my message, on a condition on the function theta, so on the growth of the LP norms, okay? Which is rather implicit, but one can do a couple of examples. So if omega has a blow up, as a logarithmic blow up, then the function theta grows like p, then the function psi is like log, and then no Osgood property, and then the argument does not give uniqueness. So if omega has a log-log singularity, then theta grows like log of p, and then psi now becomes a log-log Osgood condition. Okay. So Yudovich results on these two special cases of log or concatenations of logs gives a uniqueness for a log-log singularity of the vorticity, but not for a log singularity of the vorticity, which is fair enough. Well, but omega, so log of x, is the typical BMO singularity. So if you look at the type of blow up, so a BMO function does not need to be L infinity, can have blow ups, and the typical one is like log of x. So this motivates why the log is, so BMO is not covered by Yudovich's trick. So let me make two observations, which will lead me to our result, or to our way of seeing this problem, this question. So Yudovich's proof first makes essential use of Calderon-Zygmund. So it really uses the form, so the bound on the constant in the Calderon-Zygmund inequality for that special operator. Second, okay, on some concatenation of logs, you can express explicitly the function psi and check whether it sounds good or not, but still it's a quite implicit condition. Okay, so you have theta, and then you construct psi, and then from psi you ask, okay, does the integral in the Osgood condition diverge or not? So it's rather implicit. So what we did is we went back to this old problem in a sense, and then so we produced the result, which I am going now to tell you. So our result has the following, say, elements, if I have to comment on it. So first, we don't use any Calderon-Zygmund theory. We don't even use Sobolev spaces in our paper. So we do a PDE theory in which we completely avoid any use of this type of functional spaces. So we have a sort of more, say, metric approach, and we carry out a Lagrangian proof more than an energetic proof at the PDE level. Second, the uniqueness condition, that's I think the big plus of our approach. The uniqueness condition on the function theta becomes more explicit. So it's no longer via this infimization process like in Yudovich. Then another benefit of our work is that we can work in so-called uniformly localized Yudovich spaces. So these are the following objects. So in this Yudovich theta spaces, without this UL, uniformly localized, one was asking for a condition depending on this function theta on the growth of the global LP norms of the function. Now we can live with the so-called uniformly localized LP norms, okay? FLP uniformly localized is the following. So you look at the LP norm on bolts of a fixed size, so 1, radius 1, and then you do that uniformly with respect to this center, okay? So it's localized and it's uniformly localized, okay? So in bolts of a fixed radius, but uniformly with respect to the point. Then this y theta UL, so uniformly localized Yudovich spaces, are defined by this condition. So the uniformly localized norm grows like theta of p. And the main lemma that we provide is an explicit modulus of continuity for the velocity, okay? So modulus of continuity is, okay, v of x minus something which controls increments in the velocity. I'm gonna call it phi theta, and this depends in a rather explicit way on the function theta. And the way is very explicit, okay? So it's very explicit in that it's r times 1 minus log of r, which we already saw at the very beginning when I said what happens for L infinity vorticities. Then we have some additional degeneration or blow up in a sense of our possible blow up of the modulus of continuity or less good continuity at the origin by again some logarithmic dependence on the distance, but for this function theta, so theta of the log. So it's a sort of, instead of log Lipschitz, is log theta log Lipschitz in a certain sense. And okay, so V is also bounded, so V stays as bounded. So remarks on the result. So if omega is in L infinity, then the function theta, so the growth function, is bounded, and then we recover with our proof the log Lipschitz case. So our computation have a certain similarities that with some computation that Evelyn Mio did a few years back for the Vlasov-Poisson equation, which is again an equation which has a transport-like structure, but it's a kinetic equation. The computation have a similar flavor, but she remarked explicitly that the approach that she has does not apply to the Euler equation. So she really makes use of the split structure that she has because she has a kinetic problem, so inherently of second order for what you look. So when you look at the characteristics, okay. Then the sort of special thing, so I was mentioning this elementary metric approach. So we don't really need any, any special formula for the recipe, which given the vorticity gives to you the velocity. So we just need some integral operator with a convolution kernel, so a convolution operator with some k of xy, where k satisfies two conditions, which are indeed satisfied by the Biot-Savart kernel in R2. So a blow up, okay? So when the two variables coincide, so there is a blow up, like 1 over the distance. Then there is an oscillation or regularity estimate. So in the first variable, we are sort of Lipschitz, with a degeneracy when we go to the singularities, okay? Like 1 over x minus z was my y minus z. So the domain can be basically whatever. So in a certain sense, the domain is not really important, not even the regularity of the domain, apart from the fact that if you want to treat the Euler equations, once you have a domain, you have a green function, and then you have the kernel associated with that green function, and then it has to satisfy the two conditions that I was mentioning. So in a certain sense, the regularity of the domain is implicitly assumed when we assume these two properties for the convolution kernel. And then we can also relax the incompressibility condition, but that's not something very relevant, and I will not stress that. And again, the main computation is extremely simple, and it just relies on very elementary integral estimates in real variable. Okay, so I want to estimate the increment between 2 points in my domain omega. I call d their distance. I look at the regime in which the distance is less than 1. It's a modulus of continuity estimate. Great. So I just write explicitly what I have. I estimate by bringing the modulus inside the integral, and then I split. Okay, I split. So outside of a large ball, of a ball of fixed radius 2, close to the singularity at x, and the close is basically a slave to this distance here, and then intermediate range. Okay, I have these 3 things. So for the far away one, so that's a cute contribution. Okay, so here I take out using the oscillation property of the kernel, x minus y, and then I have a stuff which I can integrate. Here I am away from the singularity. I get a global L1 norm of the vorticity. So here I get the Lipschitz piece. Okay, not a big surprise. For the other 2, I do the following. So for the intermediate regime, I estimate again with the oscillation. I get a Lipschitz thing, and I get a function which I keep there for a moment. Okay, so it's the integral on this intermediate in this intermediate regime of vorticity divided by quadratic singularity, and I have a Lipschitz part in front. Close to the singularity, I neglect the fact that I have a difference. So I use the decay, and I estimate with a sum of 2 objects. Okay, so I use the following. So I don't use the difference which appears here. And again, I owe you to an estimate for this function here, which now has only linear blow up below. But I have not taken out the Lipschitz part here. Okay, so they are sort of comparable, these 2. Okay, I need to control these 2 things. So intermediate regime, quadratic down, close to the singularity, linear down. And again, this is another elementary computation. So for the first function, I just do Hölder and explicit integration. Here you see why one gets only uniformly localized norms. Okay, because here I am just integrating on some given ball. And then I get this thing here. So I just integrate radially the function 1 over x, 1 over x squared. So this is for alpha. And this, so same thing for the function beta. So here I get distance. So these are numbers depending on the p at which I am doing the computation. Here I have d to the minus 2 over p, d to the 1 minus 2 over p. But don't forget that the alpha term already had a Lipschitz coefficient, Lipschitzianity coefficient in front. Okay, then we get the following. So adding up all the previous, so considering together all the previous computations. So if p is between 2 and plus infinity, if I have some vorticity omega in L1 cap LP uniformly localized, then the associated velocity is bounded and is 1 minus 2 over p Hölder continuous with this very explicit control. Okay, so this is for the L infinity norm, which I didn't do in detail, but the one for the recalling that d was the distance between the 2 points, what I got for the Hölder control is something like this. Okay, this should not come as a surprise, because for the Biot-Savart kernel, Calderon-Zygmund theory tells that if omega is in LP, then the velocity is in W1P. For P large, there is the Morris inequality, and then you get a Holder continuity estimate exactly with this exponent. But our proof is totally elementary if I have to compare to the use of Calderon-Zygmund and Morris. So our proof is elementary, and our proof holds for kernels with more, say, more general kernels once we have those two estimates I was describing before. Okay, so this is for vorticities which are in LP uniformly localized, P larger than 2, and globally integrable, but P is fixed. So I was telling you there is this modulus of continuity if the vorticity is in y theta UL, so in the uniformly localized Yudovich space with growth function theta. Okay, so theta is a function depending on P, tells you the LP norm of the vorticity grows. So the LP norm of the vorticity is theta of P. So it tells how the vorticity grows when P goes to infinity. And this UL stays for, I just consider LP norms on ball of radius 1, but uniformly with respect to the elongation. Okay, so we arrive to this formula here, and then I write it for, say, P greater than 3. So I forget some singularities which are around in the P minus 2 denominator. I'm arguing now for P large. And here I have now, okay, I do the following. So I estimate now the LP uniformly localized with theta of P times the norm of omega in Yudovich uniformly localized. Then I have the P, which survives, and the Holder coefficient, which survives here. Okay, this holds for P, number larger than 3. Then I pick P. Okay, so I want to provide a modulus of continuity. I pick P logarithmic in the distance between the 2 points, and then I insert what I have. So here I have norms, theta of the log. Here I have P, which is the log. I take here x minus y to the 1, and here I recover what I was announcing before. So Lipschitz, log Lipschitz, and since the vortice is not L infinity, but is growing, I get a term which is again a bit more singular, so theta of the log, okay? And here I just use one magic thing, which is like any number to the minus 2 over 1 minus log of the number is uniformly bounded by logarithmic computations that you do in analysis 1. So this is bounded by e to the minus 2 for every x and y. Then I exactly proved what I announced. So my my estimate for the modulus of continuity phi theta. Okay, now we have to make a remark. So until now, there are no conditions on the growth function data. Okay, so theta can grow very fast at infinity. Okay, it just needs to be finite for every p less than infinity. It can go very fast to infinity, which corresponds to LP norms blowing up very fast at infinity. So when the exponent goes to infinity, this results in the fact that, yes, I am calling phi theta modulus of continuity, but it's a fraudulent modulus of continuity in principle in the following sense. So if theta grows very fast, here we don't need to have a function. So this function phi theta does not need to be infinitesimal when the variable goes to 0, okay? So it's not a modulus of continuity which has the value 0 at 0 and is continuous at 0, okay? So we still call it modulus of continuity in a generalized sense. It is continuous it is a real modulus of, a true modulus of continuity in the settings that we really want to consider, which are settings in which we impose some mild growth on the function data, okay? And here we enter in the applications, in a sense, to existence and uniqueness for the 2D Euler equations. So the first result is the following. So if we pick an exponent p between 2 and infinity, then for every initial theorem in vorticity L1 global cap LP uniformly localized, we have a solution which is locally uniform in time in the natural spaces. So L1 cap LP UL for the vorticity, and in this holder space for the velocity. Moreover, second result, if we start in Yudovich, uniformly localized, then our vorticity remains locally uniform in time in the same space, and the velocity now has this modulus of continuity, this phi theta modulus of continuity. So if phi theta is a bit more, so it's even Osgood, then the weak solution that we have is even Lagrangian. So until now, we're working with PDE solutions. They are solutions, if you think for a moment the velocity is given and you are transporting the velocity, this solution, they should have this property that the vorticity is really transported by the ODE flow, but we are in a weak regularity setting, so this does not need to be always the case. It is the case, in particular, if this function phi theta is as Osgood regularity. So we see again this Osgood condition, it's coming back to us in a certain sense. And these results, they should be compared to results obtained some 20 almost years ago, 18 years ago by Tanucci. So in which, okay, it did something which was very different for what concerned the techniques. So it was working like paradifferential, with paradifferential calculus. We need this global L1 condition that he didn't have. On the other hand, his techniques force him to work globally in R2. We are just, you know, it's totally fine for us to work on a given domain. Okay, so a comment on the proof, into the details of which I will not go. So here, okay, becomes a question, so which religion you are following in the following sense. So you either are just, you know, fluid dynamics, you want to work with the Euler equation, then fine, you know that you have existence of smooth solution for the 2D Euler equation if you start with nice initial data. And then you also have existence of L infinity solution if you start with L infinity vorticities. If on the other hand, you just want to, you know, remain general and do, say, a completely self-contained approach and prove existence for kernels, for convolution kernels, which don't need to be the Biot-Savart one, well, you have to basically trash all you know about existence of weak solutions for Euler, because it's mostly based in the formula I know, at least on the existence of smooth solutions, which relies on the velocity equations, on the fact that you have a PDE for the velocity, and then you start doing the regular theory there. So we don't have a velocity equation if we treat a very general kernel, and then we had to basically reprove everything from scratch, which is also quite fun in the end. You know, one goes back to very elementary things, and then one really sees also what's really needed for the, say, most hands-on and no big technology proof. So we first constructed a solution in L1 cap L infinity via time stepping. Okay, so you do a time, so you have the interval, your time horizon is 0 capital T. You subdivide in n intervals, and then on every subinterval you transport your vorticity by the velocity that you obtained from the previous step, and then you show that you can pass to the limit. Then in L1 cap LP UL by truncating the initial data, then you have some compactness. And then once you have the solution there, you basically show propagation of the quantities you want to propagate. So the LP UL and the Y data UL for the vorticity. So this becomes, you know, like 2 steps if you want. So existence in L infinity or LP UL, and then propagation of these quantities. And okay, so there are many tools, they are all sort of elementary, and what we use is, say, a variant of the classical Aubin-Lyon lemma. So Aubin-Lyon basically is this usual lemma, which is used a lot in evolutionary PDEs, which once you just have a very weak continuity in time, so Lipschitz, but with values in a very low regularity space, but you have some compactness in space, then it allows you to recover some compactness in time too. Okay, and we need such a lemma, but we need a variant of it because we need a lemma in the following form. If we have weak compactness in space and weak regularity from the time, then we recover strong in time, weak in space. And this is what we need because for the velocity, since we have this uniform continuity control, we have strong in space. Okay, so we don't need strong in space for the vorticity. We have it for the velocity. They need to couple, but then at some point we need to recover some strong compactness in time. Otherwise, we cannot pass to the limit in velocity times vorticity if we hadn't some strong compactness in time. And while this can be done by looking at some evolutionary equation for some quantity, and we only have it for the vorticity, then we use this weak, say, Aubin-Lyon lemma, which again, so we just reproved from scratch again to show how all these things are sort of quite elementary. Okay, what's probably more interesting, so is the uniqueness. So the uniqueness, and in this sense also show how this clarifies partly Yudovich result. So if theta, so the growth function for the vorticity is such that one, phi theta, so the modulus of continuity for the velocity is a concave function, and second as Osgood growth. Then there is at most one, and then there is parenthesis Lagrangian. So let's read it in this way. There is at most one Lagrangian weak solution, which remains locally uniform in time in this space. Okay, so the vorticity stays in L1 cap y theta UL, and the velocity is in this quantified continuity space. Okay, there exists at most one Lagrangian solution in this space, given the initial datum in this space. So we recover and improve Yudovich, improve mostly in the sense that we have a more explicit condition for the uniqueness. When you look at concatenation of logs, we are at the same level. Okay, so we don't largely improve the type of growth we can allow. And this proves, well, it has a sort of Lagrangian character, so it's quite close in a sense to some proof of Lepere for the L infinity case. And also Serfati had a sort of, related idea, but it was more, so I think, a comparison between velocities and not vorticities. And you also find in the book by Marchiori and Pulvirenti, you also find this type of Lagrangian proofs. Again, it's a Lagrangian proof, so no energy methods are used. And then, okay, there is this thing about the parentheses. So why is Lagrangian here in parentheses? Because, okay, what we do is we have two solutions. We assume them to be transported by a flow, and then we do our proof comparing the two flows. Okay, if I only give you two weak solutions, you obtain uniqueness only if you are able to say these two weak solutions, they come from flows. Okay, they are advected by a flow, and then I use your proof, your Lagrangian proof. So the fact is, well, this is true. So once you have an equation, a transport equation with an Osgood velocity field, then every weak solution is Lagrangian. The point is, well, this is a non-trivial thing, highly non-trivial. This has been proven in 3 different ways, or I mean, as a corollary of 3 different things, and that's complicated. So by Ambrosio Bernard with more like currents tools, Klopp and collaborators. That's another quite deep paper relying strongly on harmonic analysis. And then this also follows by, by something I was doing with Laura Caravenna a few years ago for completely other scopes. And there it's more like a real analytical proof in a certain sense. So we had some suitable, say, Lipschitz extension lemmas that we were using, and this result. So the Lagrangianity of weak solutions in this context was a corollary of that. So in a certain sense, so you can remove the word Lagrangian from my theorem. If you remove it, you have to use this quite strong results. Okay, so I give a sketch of the computations that we have in the proof, and then this will be the last thing I do in this talk. Okay, I have two vorticities, omega 1, omega 2. They are Lagrangian, so they are transported by flows, x1, x2. I write it, and then I fix 0t. I fix capital T. I compare the two flows. Okay, so the flows are such that x dot equal to v of x. And then I can estimate the difference between the flows with the difference of the velocities along the flows, time integrated. I split it, okay, v1 of x2, v1 of x2, so that I get here some increments of v1, and here it's some difference, v1 minus v2, computed at the same flow, okay, at the same place. Great. For the first term, again, it's rather easy. So I just use the phi theta continuity of the velocity. Then I estimate in this way. Okay, for the second term, well, we do quite a bit more manipulations. So the second term is an integral in time of v1 x2 minus v2 x2. Okay, I rewrite it, okay, without the time integral. I insert the formula for k of omega, which is v, as an integral. And then I start swapping things, changing variables because of the formula via push forward. And then I have to the last line, which is on the slide. Okay, so just computation. Then we combine the two computations together. Okay. In that here I have this integral here. I have the time integral which I take from before, and then I arrive to this point. Okay, now there is one thing which is slightly annoying. So if we are not on a bounded set, we have to take a sort of a reference function. So just a trick in the proof. Okay, so we have to take this eta function, which is L1 cap L infinity, but is fixed once for all, is not very relevant. So just think that you are integrating everything with respect to the total variation, so to the absolute value of the initial vorticity. Okay. And I look at what I get here for the second term. Once I do that, I can start Fubining my integrals. So I swap the order of integration, and that's what I get. The point is that I reconstruct again an integral of phi theta, so the modulus of continuity of the difference of the flows, multiplied with the modulus of the initial vorticity. Where in here, I use basically the same computations I was doing at the very beginning for the modulus of continuity, a variation of them, in fact, in which you already bring the modulus inside at the beginning. And then you change variable again, okay? And then you get this. And now we are basically at the almost last slide in that, okay, so we arrive to this type of inequality here. So both pieces, I have been able to estimate in the following way. So the integral of the difference of the flow with respect to basically this total variation of the initial measure is controlled by the integral in time of the space integral of phi theta of the difference of the two flows. Which is great because, okay, by concavity, first of all, I can, by Young, take, one level up, one level out, this phi theta. And then if I define psi of S as the difference in L1 between the two flows, integrating in the reference measure, I get an inequality like psi controlled by the time integral of phi of psi. And since phi theta is Osgood, that was our second assumption on the modulus of continuity, this gives uniqueness in the sense that since the two flows, they coincide at the initial time, the two flows are equal for all times, the two flows, and therefore the vorticities, and therefore the velocities. And this concludes the proof. proof and also concludes my talk. So thank you very much for your attention.